In this video, we are going to check if a pair of simultaneous linear congruences have solutions. So I've got my check for solutions written over here on the right. So we've got two steps to do. The first one is checking that each individual congruence relation must be solvable. Well, in this case, we can sort of skip that step because if we look at our two congruence relations, they're both in the format 1x and 1x is congruent to some numerical value. So therefore, the solutions of the individual congruence relations have already been found. So we can be sure there are going to be solutions for the individual congruence relations. So I'm just going to put a tick here. Now let's consider step 2, which involves looking at the highest common factor of our two mods. So I'm going to look at the highest common factor of the 6 and the 4. Okay, so the highest common factor of 6 and 4, well, that's equal to 2. Then we're going to check if this 2 that I found here is a factor of the difference between the 5 and the 1, which are the two values I haven't used yet. So we're going to do 5 subtract 1, or you could do 1 subtract 5. You're just going to get the negative of the other result. So 5 subtract 1 is equal to 4. Well, is 2 a factor of 4? Well, yes, because 4 can be written as 2 multiplied by 2. So I can say, therefore, the highest common factor of 6 and 4 is a factor of 5 subtract 1. And then we can say, therefore, solutions exist. Now, what I'm going to do next is actually follow through and try and solve these because I want to just investigate how the mod of our answer relates to the initial mods in the question. So to start the process of solving, I'm going to take one of my congruence relations. So I'm just going to take this one here and we're going to convert it to an equation. So we would get x is equal to, and it'll be our mod 6 multiplied by some integer we'll call t plus 5 our remainder. Okay, and that is where t is an integer. Then we are going to substitute what we've got for x, so the 6t plus 5, in place of the x in the other congruence relation I haven't used yet. So I would get 6t plus 5 is congruent to the 1 mod 4. Then we're going to rearrange to get the t term on its own, so we're going to subtract 5 from both sides. So I would get 6t is congruent to negative 4 mod 4. So now what we usually do next is try and get it so the numerical value multiplying the t and the numerical value on the other side are the least positive residue. Well, from the 6, we can subtract 4, our mod, so we would get 2t is congruent to, and then for our negative number, we'd have to add, well, if I add 4, I get 0, which isn't technically positive, but if I add 4 again, then we're equal to the mod. So actually, I'm going to leave it at 0, and technically, even though I usually call it the least positive residue, another way of thinking about it is the least non-negative residue, okay, because 0 isn't a positive number, but it would be considered the remainder, because the remainder can be any value up until 4, but not including 4, but you can include 0. So then I'd write in the mod 4. Then usually what we'd do next is investigate the highest common factor of the value multiplying t, so the 2, and the mod, which is 4. Well, the highest common factor of 2 and 4 is equal to 2. So I've ended up with the same value here as I had over here for this highest common factor, which we'll find actually is logical, because if we consider the two values we are trying to find the highest common factor of here, the 2 and the 4, well, this 4, that's just the mod here, which was the mod in the initial question, 4. And then the 2 here, well, that comes from the 2 multiplying the t, which is just a reduced version of the 6 multiplying the t, which is the original mod in the question 6. So logically, the highest common factor that I get here should be the same as the highest common factor I had from the mods over here. But what we'd do next is, because this value here is not 1, we'd check if it's a factor of the 0. However, this step is also redundant in this case, because the 0 is just a simplified version of the negative 4. And the negative 4 came from the 1 here, subtract this 5. And that 1 and 5 came from the initial mods. And if we look at what we did earlier, we already subtracted those values over here and checked that the highest common factor of the 6 and the 4, which is equal to this 2 here, was a factor of the 5 subtract 1. So therefore, this whole step that I'm doing here is not necessary when solving simultaneous congruences, providing you have done this check over here earlier on. Now, usually we'd divide the congruence relation by this value 2 next, which is essentially dividing the congruence relation by this 2 over here. So that's just the step we need to remember to do using that highest common factor. So let's take this part off because we never really needed it. Okay, let's divide my whole congruence relation by this 2 over here. So dividing by 2, and importantly dividing our mod by 2 in this step, we would get 1t is congruent to 0, and it will be mod 2. Now, usually what we try and do is give our solutions for t in terms of the original mod, which was 4. Okay. However, because we're trying to solve simultaneous congruences, the mod here isn't that important because remember, we're trying to solve this pair of congruence relations up here. So what I'm going to do next is try and convert this congruence relation here into an equation for t. So we'd have t is equal to our mod, which is 2, multiplied by some integer I'll call k, and then plus our remainder, which is 0. So I don't need to add that on. And I just need to state that k is an integer. And then my next step was to take the t equals 2k and substitute this in for the t up here. So I would get x is equal to 6 multiplied by 2k and then plus 5. And if we simplify, we get x is equal to 12k plus 5. And we're just going to state where k is an integer. Then we can convert this information back into a congruence relation. I can say that x is congruent to, and our remainder is the 5. So I'd write a 5. And then our mod is the value multiplying the k, which is 12, like that. Now I do just want to investigate how this mod 12 links to the initial mods 6 and 4. Well, if I do 6 multiplied by 4, that gives me 24. And then if we divide that value by the highest common factor of our mods, which was 2, well, that's going to give me 12, which is this value here. And that is how you figure out what your final mod should be. So it's a convenient way of just checking you've done things correctly. And let's just relate the dividing by 2 to our process of solving. Well, it's to do with this step here where we divide the mod by 2. Because as a result, we get 2k here as opposed to 4k. And that carries over to when we substitute into the 6t up here. And as a result, from this product, we get 12k as opposed to 24k. And another way of thinking about this 12 and this calculation in general is that the 12 is the lowest common multiple of our initial mods, which were 6 and 4. So if you multiply two values together and then divide them by their highest common factor, you are essentially finding the lowest common multiple. So if solutions exist, the final mod will be the lowest common multiple of the initial mods. Now let's have a look at another question where we're going to check if solutions exist. So here's our next one, and we need to determine if there are solutions to these two congruence relations here. Now, step 1 is to check that each individual congruence relation is solvable. Once again, we have 1x here and 1x here, so therefore they're already solved, so step 1 is essentially already done for us. Now let's consider step 2, which is finding the highest common factor of our two mods, so the 15 and the 10. Well, the highest common factor of 15 and 10 would be equal to 5. Then what we're going to do is make use of the two numerical values we haven't used yet, so the 7 and the 5. We're going to consider the difference between these two values. So 7 subtract 5 is equal to 2. Now, is our highest common factor 5 a factor of 2? No, it's not. We'd say 5 is not a factor of 2. So therefore, there are no solutions. Let's consider one more scenario. So once again, we need to determine if there are solutions for these two congruence relations here. They're once again in the format 1x and 1x, so they're already solved, so step 1 is already done. We just have to consider step 2. So let's investigate our mods, so 11 and 10. What's the highest common factor of 11 and 10? Well, it's 1. Okay, they are co-prime. Now let's consider the two numerical values we haven't used yet, so the 7 and the 5. Let's consider the difference, so 7 subtract 5 is equal to 2. Now, is the 1, our highest common factor, a factor of 2? Well, yes, it is. Okay, so we can say that 1 is a factor of 2, so therefore solutions exist. And of course, 1 is a factor of any integer. So essentially what we've determined here is that if our mods are co-prime, if the highest common factor comes out as 1, you can be sure there'll definitely be solutions to our simultaneous congruence relations. The final thing I want to consider is what is the mod of our answer. Well, we said to find that we needed to find the lowest common multiple of our mods, and to do that we can do 11 multiplied by 10, so the product of our mods, and then divide by the highest common factor, which we determined to be 1. Well, that comes out as 110. And of course, the dividing by 1 is redundant, because if you divide by 1, you're not going to change the value of the numerator. So essentially what we've determined is that if our mods are co-prime, so if they have a highest common factor of 1, then the mod of our answer will just be the product of the initial mods, which in this case is the 110.